Well, here I am again. You get a nice video from Kleiber this weekend. And what we're going to be talking about is the topic average rate of change and also average value. Because I noticed after grading your free response questions of your last practice exam, there were quite a few mistakes on this. So let's get started. First of all, average rate of change. We've learned this actually in Algebra 1. This is basically calculating the slope of a function when you are given the original function. And that is known to be the change in y over the change in x. So an example problem, let's say you have to find the average rate of change of a function f on the interval ab. So we know this to be f of b minus f of a, which is the change in y, over b minus a, which is the change in x. Now let's say that you're given a position function. So this is a very specific type of problem. Many times it's abbreviated as a position, velocity, acceleration problem. And we want to find the average velocity. So we're wanting to find the slope of position. So for average velocity, we would go x of t sub 2 minus x of t sub 1 all over t of 2 minus t sub 1. But actually, you know what? To be completely accurate, shouldn't we use the function s of t? So it would be s of t sub 2 minus s of t sub 1 minus t sub 2 minus t sub 1. So you can see common notation for position is either in the s of t form or the x of t form. Okay, let's look at a couple examples here. Now I don't necessarily want you to solve them. I just want you to be able to set it up given the information. So we are told that the position of a particle, so we're given position on the x-axis at a certain time t, where t must be greater than 0, is the natural log of t. So that's my position function. So what would be the average velocity between 1 and e? Well, again, we'd go the natural log of e. Why did I put a 2 there? I don't know. Natural log of e minus the natural log of 1 all over e minus 1. Moving right along, we have another movement problem. We have a particle that's moving along the x-axis, so that its position, again, you're given position, is given by this function. At what time is the average velocity 0? So we want to find the time when average velocity is 0. Well, since it's average velocity, again, we're going to go x of t sub 2 minus x of t sub 1. Whoops, sorry, that was a little wacky on the parentheses. All over t sub 2 minus t sub 1. Okay, well, our ending position, we don't know that. That's the unknown. And we're going to begin when t is 0, and it's all over t minus 0. Now we want this to be equal to 0. Well, since it's a rational expression equal to 0, that means we want the numerator equal to 0. And then we can just start substituting the facts that we know. We're trying to solve for x of t, and we know that x of 0 at time 0, if I plug that back into this original position function, we would just get 0. So then we would set that function equal to 0 and use our zero product property and solve for t. Fantastic. Now I'm going to use my handy dandy eraser to give myself a little more room to do the third problem. Okay, so the third problem, we are given a situation when we're talking about the growth of a mass, and the time is weeks. And the function here, m of t, models the growth in grams. Actually, it's not the growth, it's not the rate of change, but it begins growing by. Okay, so this is the mass. Okay, the weight in grams of the mass. What is the average rate of change? Okay, in grams per week. So again, we would go m during the 5th week of 5 minus m of 0 all over 5 minus 0 to give us the average rate of change in grams per week. Now remember, when you're answering these questions, use actually the phrasing in the problem. It's like if you got 20, then you would say it's changing, the average rate of change is 20 grams per week in the 5th week of growth. Okay? Now, what was given to you in each of these problems? The function was given to you, whether it was a function of position or just the original function for growth of grams for a tumor. Very important to know. Now, all of those examples were were an algebraic presentation. What if you're given the numerical view? Okay, so we're given a data table. Now look specifically at what you're given. You're given the number of people that are waiting in line. Okay, so you're given the original function L of t. And we want to find what is the rate at which it was changing at 5.5. So we don't know the exact values at 5, but what we can do is we can approximate that because we want to find rate given the original function. So we would go the change in y over the change in x. So we go 115 minus 126 all over 7 minus 4. That's a numerical perspective. Okay, this is the exact problem from your test. Yes, it is. So we have a cylindrical can with a radius of 10 millimeters. Now, are you underlining the facts when you read an FRQ? You should be. This will help you in your test taking. And the can is initially empty. So at time equals 0, the value is 0. And we're going to be looking at a 60-day period from 0 to 60. The height can be modeled by the function s. So s of t will give us the height of water in the can. Okay, very important. Now it's measured in millimeters. Okay, so height in millimeters. The rate at which it's rising is given to us in an algebraic function. So that's the rate of change of height in millimeters per day. Okay, so we might want to write that, millimeters per day. Now that you understand all the facts given to you, you are asked to find the average rate of change. Well, we were given the rate of change function. So that means I want to find, so I was given s prime t. So if I want to find the average height, that means I want to find the average value since I was given the height. So you know average value to be the integral of this function from 0 to 60 all over 60 minus 0, which is 60. Now I could plug this up function in and then find that. Now another way of thinking of this, well, you want to find the average rate of change. So that means if I had the function s of t, then from s of t, we would go s of 60 minus s of 0 all over 60 minus 0. Well, do we know the height at s of 60? No, we do not. So I just am not able to use this expression to calculate the rate of change. But I am given s prime t, so I can use this expression. But you do realize, though, the integral fundamental theorem says the integral of a rate of change is equal to its original function, s of 60 minus s of 0. So notice these two expressions here are equivalent, but only one of them is provided with information in the problem. Okay, now, again, this is another problem, but we had this in our last FRQ practice test. And here we are told we have a 12,000, we have a 12,000 liter tank, and at time t equals 0, it will begin to drain at a rate modeled by R of t. So this is the rate at which it's draining, and this is liters, that's kind of spelling, per hour. So this is a rate of change function, okay? Now you have to find the average rate between 0 to 8. Now again, I'm given the rate. I'm not given the original function. So since I'm given the rate, then I need to go from 0 to 8 of R of t all over 8. Now since it's piecewise, we must divide it up into two pieces, which you could do, right? From 0 to 5 of that function, blah, 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 you finish the blanks, plus from 5 to 8 of that function, blah, 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 you finish in the blanks, all over 8. Okay, great. I hope you're getting this. Now, you actually, oh, darn it, did you notice how the last problem was numbered 1? Well, that's the problem you have to finish on your own, and then show all of your work on a piece of paper, and then submit your answer on the Google form on the website. Now notice this is problem 2, and problem 3. So your responsibility, again, is to work these out on a piece of paper and then submit your answers on the Google form. Please bring your work to class the next day. But realize what you're given here. You're told f of x is equal to the integral of 0 to x of the function cosine of t squared plus t plus 1. So you're going to have to use your fundamental theorem to answer these two questions about average rate of change. Now be very careful. You might want to look at your yellow resource page, especially in respect to fundamental theorem and so forth. Okay, mean value theorem for integrals. Now we've talked about the mean value theorem for derivative lots. Remember, if a function is continuous, blah, 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 blah. Yep, that was for derivatives, folks. But now if you're trying to find the area under a curve between x equals a and x equals b, okay, area under a curve between x of a equals x of b for this function f, then there has to exist a number c whose function value you can form a rectangle that is equal to the area under the curve. So in other words, this gray shaded area here, the area of that rectangle, is equal to the area under the curve. What is the expression that can be used to determine the area? Well, that's an integral. The integral of a to b of the function f is the area under the curve. What would be the area of the shaded rectangle? Well, area of a rectangle is its height times the length, which would be b minus a. So we know by the mean value theorem that this area of a rectangle has to be equivalent to the area under the curve. So the integral of a to b of my function f. So we can see that this average value theorem is coming from this, the integral from a to b of the function f all over b minus a. Okay, so the value of f of c is the average value of the function f in the interval a to b. Right there for you, something we learned a while ago. Now let's apply this. So if a function is continuous on some interval a to b, then there has to exist a point c on the interval. The average value has to exist. Now again, going back to one of your questions you did on the test, the radius is 10, and we are given the rate of change in millimeters per day. So you had to explain this expression in context of the problem. So what are we finding? Well, we are finding the average value of s of t. Okay, now what is s of t? Well, s prime t is the change in millimeters per day. So s of d is the height of the water in millimeters. Okay, so then this would be the average height of the water. Oops, sorry for my spelling there. Average height of water, and in millimeters, oh my word, in millimeters during, or the average height of water in millimeters between 0 to 60 days. Okay? Does that make sense? Now what if I were to change this problem? So instead of it being the integral of s of t, what if it was the integral of s prime t? Okay, how would you interpret that in context of the problem? 0 to 60 of s prime t. Okay, well we know s prime t is the height of water rising in millimeters per day. So this would be the answer would be the average rate of change So you'd find the average rate of change, and then, like, let's say your answer is, it would be either is increasing or decreasing, depending if you got a positive or number answer, at the rate of something per millimeters squared per day. Okay, so this would be the average rate of change is increasing or decreasing at a rate of blank millimeters squared per day. Make sure you understand the difference in that. Many put that on your test. Okay, now these two questions you have to answer on your own. So now you're seeing a numerical perspective, and looking at the numerical perspective, you have to be able to approximate the rate, and then you have to approximate the value of that expression, and then explain it using the correct units. Fantastic. Okay, and again, 3 more questions given a tabular view of a problem, and you have to find the instantaneous rate at 7. You have to use a trapezoidal sum, and you have to find the average temperature of the wire, and then you have to interpret this expression in context of the problem. And that is it for today. We'll be talking to you soon.